First thing I want to talk about, recently, of course, SIGGRAPH was held, and they had a number of papers that were presented there. And this is the SIGGRAPH 2026 Best Paper. And so this is published in ACM Transactions on Graphics. And so this is something called Mixwell, sharp 2D fluid brushes for progressive physics-based mixing. So, at SIGGRAPH, they introduce a bunch of techniques, and, they work the techniques out, and then usually that's where people go to build tools for the next generation of image processing and computer graphics. So this is their website for the paper. They have the paper, the supplement, the video, and the talk. I like the way this is set up. And then they have the citation here in BibTeX and on the ACM. So this is going to just be kind of a description, and then there's some demos here that you can explore. So the abstract reads, we present Mixwell, a family of sharp two-dimensional fluid brushes and GPU-accelerated analytical methods for progressive resolution-independent physics-based modeling, or mixing, derived from idealized potential flow around a cylindrical tine. Mixwell includes a cusped Kelvin-Lutz style regularized velocity brush that parsimoniously captures cylinder fluid interactions. Building on Maxwell's 1869 drift formulation, we developed GPU-friendly evaluation strategies for particle drift in both infinite and finite strokes. So this is a lot of technical detail, which I'll open the paper and we can look at. For image-based workflows, we introduced cylindrical reverse drift functions, or RDFs, displacement fields that encode time insertion, motion, and removal. Like sign distance fields in geometric modeling, RDFs compose naturally and can be chained in shaders to model complex operations while avoiding intermediate texture blur. We also propose a periodically exploiting composition scheme for complex RDF patterns. All Mixwell operations are evaluated independently per sample, enabling truly progressive mixing and rendering without global solves, grids, or intermediate texture resampling. We demonstrate real-time GLSL and HLSL implementations and production integrations in Houdini, enabling progressive arbitrary resolution mixing and rendering with negligible numeric dissipation. So this is kind of an example of the mixing patterns that they have here. So it does look like a kind of a fluid dynamics thing where they're mixing patterns and colors in these ways. So let's go to the paper. Okay, so this is Doug James from Stanford, and Ethan James is an independent researcher. And so this is, this figure 1 is what we saw on the website. Progressive simulation of rendering in 2D fluid mixing. We have these Mixwell brushes that allow for different types of flows and modeling those as they interact with one another. Okay, so they talk about fluidic sculpting and mixing tools. So this is the class of tools that they're trying to develop an improvement upon. Fluidic sculpting and mixing tools are visually striking elements of modern modeling and animation workflows. Ad hoc geometric deformers can produce fluid-like effects inexpensively, but they often lack physical realism and incompressibility control. Physics-based fluid simulation can offer high realism and incompressibility, but it is computationally expensive, resolution limited, and prone to numerical dissipation and blur. And so then they talk about, in the abstract, they talked about Kelvin-Lutz, which are these analytical deformation brushes. or it's a class of analytical deformation brush. They provide elegant closed-form flow fields, but do not precisely model fluid brush mixing interactions, and long strokes still require fine time stepping. In short, we lack a sharp, controllable, incompressible two-dimensional fluid brush that captures precise physical, time-like flow interactions and supports detailed arbitrary resolution fluid effects with negligible dissipation and blur at real-time rates. So that's what Mixwell is serving the purpose of. It's a special purpose family of sharp two-dimensional fluid brushes derived directly from idealized potential flow around an inserted cylindrical tine. And then this is just kind of where they were drawing from in the abstract. Let's see. So they talk about the contributions here. This paper contributes 5 things to the field. The first is a sharp cylinder-derived incompressible 2D velocity brush suitable for Kelvin-LUT style interaction. The second is that we have position-level advection schemes for finite and infinite strokes based on drift coordinates. 3, GPU-efficient evaluation strategies enabling progressive simulation and rendering of fluid brush effects. Then number 4, we have these stroke-based reverse drift functions, or RDFs, with insertion and removal, supporting composable, blur-free image space mixing. And then 5 is a periodicity exploiting reverse drift function composition scheme for efficient modeling of complex repeated mixing patterns. So some very specific aims there. And I find it interesting that when you visit computer graphics research as opposed to say like AI research, their aims are a little bit different, but actually not as much as you would think. They're actually trying to do the same types of evaluation and developing different mathematical tools. So there's a bunch of related work. The first is marbling and drift. So of course, when you're dealing with computer graphics, you're dealing with sometimes ancient artistic techniques and trying to replicate those on a computer. So the first thing they mentioned in their related work section is marbling and drift. So marbling is an ancient art practiced across many cultures with a well-documented history. The Maxwell connection is mathematical and direct. So in 1869, Maxwell modeled the 2D displacement of a fluid particle due to a passing cylinder using elliptical integrals, and explicitly suggested that the induced drift is a model for paper marbling. He even rendered a marble grid by hand, noting that if a maker of a marbled paper were to rule the surface of his bath with straight lines of paint at right angles, and then draw a cylindrical ruler through the bath up to the middle, and apply the painted lines to his paper, he would produce the design shown here. And this is actually James Clerk Maxwell, of course, is known for electrodynamics and other work, including the Maxwell's Demon. This is his sort of example here of what he was just talking about. So this marbled effect. See, it's like you have a marble that's moving through a fluid flow. So the marble is here, it's moving through the fluid flow here. And it's creating this deformation around it in the space surrounding the marble's movement, or the marble's moving against the flow, and it's creating this deformation accordingly. Later, Darwin, not Charles Darwin, independently advanced these net particle drift calculations, making them widely known. And the phenomena is often discussed as Darwin or Darwinian drift, despite Maxwell's earlier cylinder analysis. We revisit classical analytical drift techniques, adapt them for GPU simulation, and introduce a novel brush for Mixwell flow, modeling that enables fast and robust GPU drift simulation without elliptic integrals. For the classical drift model, we model the surrounding flow using classical potential flow, which is the incompressible irrotational motion of an inviscid fluid past an infinitely long cylinder. So this is where they're using this different types of flow to characterize this process here. Okay. While the velocity field and streamlines are readily available, computing particle travel times and the resulting net displacement in closed form leads to elliptic integrals and semi-implicit relations. We evaluate these integrals using Carlson's symmetric integral forms and a custom Newton solver, both well suited for GPU evaluation, and compare them to the Mixwell brush advection scheme. So then they talk about deformation brushes, which are much more recently developed. This is basically this idea of interactive editing as the composition of local deformation tools. So this is something that has been around for quite a while in computer graphics. Early swept tool deformers include sweepers and swirling sweepers, regularized Kelvinlets, and other tools. Regularized Kelvinlets in particular provide closed-form elastic deformation brushes derived as fundamental solutions of linear elasticity and incompressible fluid flow. So they're Kelvinlets, they're Stokeslets, and other things. So these are like, when you talk about Stokes flows and things like that, those are related to Stokeslets. Kelvinlets are related to this definition here. These physics-based brushes smoothly drag a local neighborhood along with the flow using a blob of force. So you have this blob of force, kind of like the marble that we saw in the last image, and you're dragging along this neighborhood of, I guess, cells or particles. And so it's kind of like moving this with the cylinder. So it's like moving things along with that object. Now you can do that, of course, and it works to some extent. It gives you a nice nice visual effect, and it models the physics as you might see them in a flow. But they do not specifically model the flow around a cylinder. So just because you can generate an image doesn't mean that it actually models the flow itself. And what that means is that there is no circular exclusion domain, that material flows around at different rates, including inducing singular drift. Surprisingly, the closest Kelvinlet approximation to our Mixwell brush is a two-dimensional cusped Laplacian Kelvinlet, which has an ad hoc construction but exhibits a similar asymptotic cusp profile and far-field decay rate after suitable parameter fitting. So that's a little bit about the Laplacian Kelvinet. However, Kelvinlets are primarily used as displacement-based deformers for sculpting in space deformation. And then, of course, there are other people like Hedinger and Gastal who investigated real-time image deformation and video time warping using Newton-based inversion of regularized Kelvinlet brushes, which work best for small and smooth deformations but can incur image blur during sampling. Such approaches are less appealing for large and more sharp deformations or multi-brush interactions and complex mixing processes, all of which are difficult to invert numerically. Mixwell targets a complementary regime. So that is sharp, incompressible two-dimensional fluidic brushes whose velocity fields are specifically derived from ideal cylindrical flow, which can then be used to construct cylindrical RDFs, which we defined earlier, for texture advection using reverse time advection solvers, and support arbitrarily long brush strokes without time step-induced image blur. We rely on reverse time integration, cylindrical RDFs, and other techniques to perform large time texture advection and reduce image blur. Progressive quasi-static evaluation has been explored for cloth and shells, and for fluids via adaptive grids and multi-scalar reduced order enrichments. In contrast, Mixwell's 2D drift model admits accurate point-wise resolution-independent evaluation, allowing fluid deformation and rendering to be computed together progressively. Then they talk about analytical mixing flows, digital marbling systems, which is, we'll come back to that in a minute, image advection and blur avoidance, and characteristic map and flow math methods. So reviewing all these areas to get to sort of what they're doing here. Digital marbling systems are particularly interesting. Let's talk about that. And then maybe a little bit about flow maps, as this kind of relate to some of the things going on in machine learning, actually. So digital marbling systems are kind of like the marbling systems in art, and the sort of the 19th century and previous explorations of that. So there's a long history of digital marbling in graphics, but no analytical, physics-based, incompressible mixing brush has emerged that is consistent with cylinder flow. Geological marble patterns are commonly approximated using procedural noise. So this includes Perlin noise, and this is something that again, if you see something in nature, trying to approximate it, and trying to maybe not lock onto the process that created it, but lock onto some analog that can describe that pattern sufficiently. For 2D hydrographic marbling, the direct numeric simulation of the 2D Navier-Stokes equations have been explored for 2 decades. This has been done with something called stable fluids. However, these early systems suffered from numerical dissipation, blurring, and limited resolution. Subsequent work explored GPU-accelerated Poisson solvers and better advection schemes, as they mention here with the acronyms, culminating in Atelier M++ with GPU-accelerated USCIP and edge-enhancing filters to reduce blur. Vector graphics approaches preserve sharp contours but remain limited by their underlying coarse fluid grids. And so there's also mathematical marbling work, which proposed closed-form tool functions under incompressible, immiscible two-dimensional ink assumptions, emphasizing sharp contours, tractable inverses, and GPU backward mapping for real-time feedback. Their radial ink drop insertion model is based on an equal area argument and is similar to our time insertion removal maps. This paper also introduces a sharp stylus-like brush that does not satisfy the incompressible flow assumption for finite strokes and is in fact what they call a grab brush. So in contrast, the Mixwell brush is derived as the physical pullback of the ideal cylinder flows velocity field through the area-preserving time insertion removal map, yielding incompressible Mixwell flow. And they compare that later in the paper. We derive both a sharp Kelvinlet style fluid brush and advection scheme for finite incompressible brush strokes, supporting image deformations of arbitrary resolution. And of course, they also have computationally hydrographic printing techniques that can simulate and correct for texture distortion when dipping objects into a water bath with an inkjet printed PVA film layer modeled as an elastic membrane, enabling precise alignment of surface textures on complex 3D surfaces. This is interesting work, like kind of going beyond just kind of generating things on a computer screen where you can actually print out the patterns using different methods. This other area that they review, which is characteristic map and flow map methods, is interesting because it deals with some things going on in machine learning and physics-inspired machine learning in particular. So again, we're dealing with fluid flows and fluid dynamics necessarily. And so we're trying to create these different types of flow maps and other things that can approximate patterns we find in nature. So these strategies belong to a class of methods for representing fluid transport as a composable flow map, rooted in the classical method of characteristics and applied to a 2D transient fluid flow as early as Weigert and Wiley, which is in 1976. Tessendorf and Pelfrey, 2011, later brought the term characteristic map to graphics, framing it as a generalization of gridless advection and the scheme above. In computational physics, the characteristic mapping method evolves a long-time flow map is a composition of accurate short-time submaps, achieving high-order resolution on coarse grids for linear advection. And the 2D incompressible Euler equations, and that was, In computer graphics, many recent works have explored this perspective. BIMOC squared evolves bidirectional mappings on grids, covector and impulse formulations, advect velocity like covector quantities along the map to preserve circulation. Neural flow maps encode the spatiotemporal velocity field implicitly for long-term bidirectional advection. Particle flow maps assemble accurate long-range maps for Lagrangian particle trajectories, and Eulerian vortex methods advect vorticity along flow maps. In contrast, Mixwell's RDFs are built from semi-closed form analytical drift maps for potential flow around a cylinder rather than numerically integrating maps from a simulated velocity field. Mixwell is therefore not a Navier-Stokes solver and is restricted to the specialized 2D quasi-static brush setting we target, but it admits pointwise resolution-independent map evaluation with no per-step integration error in the infinite stroke case and supports fast GPU shader evaluation. So this talks about different aspects of idealized cylinder flow. It gives the mathematics for that. It talks about Maxwell drift and time along streamlines. It talks about that for the equations on that. Classic analytical solution for drift. So we're doing a lot of things with drift. 2D drift for infinite and finite strokes. Infinite strokes and finite strokes. And they give the mathematics here. This section are figures that show some of the sort of the calculations in graphical form. So this shows Maxwell's time and drift curves for a unit cylinder moving to the right at some unit velocity of 1.0. So this just shows that the flow is going in this direction. The movement of this cylinder is to the right, and it's advecting in this way. And then this shows the different coordinate systems, so representing the cylinder and the flow in different coordinates, and its rotational field in different coordinates. And then some of these are graphs that show the magnitude of drift and other things going on there. Then they model finite strokes, which they're doing. I think doing this in Mathematica, so they show the math for that, and then all these different simulations are done in Mathematica. They have to define the math so that you know kind of what it's doing. And then they discuss these outputs. So this is this is the 2D drift illustration, just showing drift. And then They show the Mixwell brush deformation, which is in figure 7. This is a bird-like figure marbled on a modest high-dimensional resolution raster using a real-time shader toy implementation. So this is going from this cylinder to this bird-like figure by this process. So it kind of goes from the cylinder, this set of concentric circles, and then that's deformed along the edges, forming the body of the bird, and then forming some other aspects of something that looks like a bird. So you see that this process of diffusion and advection produces this pattern.